So previously, we've been looking at mathematical calculations with our variables using volume, how it relates to pressure, how volume relates to temperature, and how pressure relates to temperature, and how pressure relates to volume. All three of these variables, including moles, which have to stay constant, are used basically in the combined gas law formula. Understand that moles are constant, and we can look at these three variables interchangeably in this formula. And it's written for you called the combined gas law formula in table T of your reference table. So let's go there now. And in table T, in your last page of your reference table, if you scroll down, you will see that there is a combined gas law. And there is the formula. And if you notice, they give you the ones for the current scenario, and they give you the twos for what I call the future. Okay? So that is the combined gas law, and there's only one. And what I did teach you was that previously, if you had a variable besides moles, which has to be held constant, the number of particles for this formula, if you had one of these variables listed that was constant, we would just cancel them out and we have a new formula. Case in point, if we dealt with pressure and temperature, sometimes called Gay-Lussac's law, we would cross out the volume, okay? If I can do that, all right, we can cross out the volume here, and at some point I can do it. We'd cross out the volume, and you're left with P over T and P over T. The ones are, again, are the current, and the twos are the future, if you want to use that. There will be some problems where you're not crossing out a constant. In fact, there will be problems where you have volume, pressure, temperature already in the problem. So the only thing constant will be moles, although they will not say that in the combined gas law formula. So again, we've dealt previously in Boyle's law where we crossed out temperature because temperature and moles are constant with pressure volume inversely related. There were the Charles law problems where we crossed out pressure was constant, so we crossed that out and we had our volume temperature relationship. And then we dealt with Gay-Lussac's law where we crossed out volume. We had pressure temperature relationships that were of course direct, like Charles law. Now we're dealing with gas law problems where we're not going to cross out any variable. We're going to use all of them to solve the problem. So the math is very similar. There's just more of it because there's an extra variable. So let's go right to the problem, and let's go to number 7 here of your worksheet. Let me model this for you. Again, you have to separate those variables that go together as the current scenario, sometimes labeled as V1, P1, and T1, and then of course the variables that are the new variables, the new changing, the dynamic changing, or the new, or I like to say the future, okay? So T2. Now, I'm not a big fan of ones and twos. I like to think of one scenario as the what? As the current scenario, and the other as the future. So in any case, it doesn't matter how you look at it. Let's plug it in. If a gas under this pressure, that's the current pressure, so I'm going to write that as 239.4 kilopascals, sometimes called kPa, yeah, and that's my pressure, has a volume of 13 liters, okay, at 5 degrees Celsius. So we know that all of these go together. There's the pressure, there's the volume, there's the temperature. However, remember that we cannot use a Celsius temperature. We need an absolute scale that tells me how many degrees away from no more motion. This is 5 degrees away from a 0 in Celsius that has plenty of motion left. So we have to convert. So Kelvin equals my Celsius, which is 5, plus 273. And what that gives me is 278 kelvins. And that's what goes here. We have to convert to Kelvin in our gas law formula because we need a temperature scale or a variable that reflects that we're 278 away from no more motion, not 5. That won't work. Okay, continuing on our problem. Okay, the temperature is decreased to -20 while the pressure decreases, I probably should say, well, it decreases to 220. So the pressure went down to 220.3 kilopascals. They want to know what the new volume is, and they told me that the what? The temperature now is -20. So Kelvin equals -20 plus 273. And if you forget how to convert to Kelvin, this formula, Kelvin equals Celsius plus 273, is given to you also in table T. So when we do this, 20 minus 273 is 253. All right, it's 20 degrees less. So this is 253 Kelvin. And all I did was just plug in the variables, the ones that were given to us in the current scenario, and here are new temperature, new pressure, what's the new volume. So this was reading, if I have a gas at 13 liters, at 239.4 kilopascals, at this temperature, if I was to change the pressure, in this case drop it a little bit, and drop the temperature a little bit, what's the new volume, the new circumstance? So the first thing we're going to do is going to rearrange our volumes. We're going to put volume by itself. I don't want you to crisscross and just find an answer that doesn't make any sense without using units. I want you to rearrange this formula. That's how big boy and big girl science is done. Okay? Now, we know this number on top algebraically would go to the bottom because I would times this side by 1 over 220.3 kilopascals. And I would times this side by 1 over. Here it would cancel. So I hope you can see that shortcut I'm using algebraically is just how we would solve for it. So in any case, 220.3 goes to the bottom here. Kilopascals. And 253 would go to the top for the same reasoning. What I'm doing is multiplying both sides by 253 over 1, and that would cancel on this side. And what I do to one side of an equation, I do to another. It's just algebra. Okay, these guys are already here, so we have 278 Kelvin. And then we have what? We still have 13 liters. That was already here. And we had 239.4 kPa or kilopascals. Okay, now I've rearranged my formula, and if I wanted to find my answer, I can just take 253 times 13 times 239.4 divided by parentheses 220.3 times 278, close the parentheses, equal. But I want you guys to give me the setup because you're going to see some what? You're going to see some answers that just give you the multiple choice like I have done. So what you do is put like over like. 253 over 278. I'm putting my kelvins over each other. 253 is already on top. So 253 stays on top. It goes over 278 Kelvin. Okay, so my kelvins are gone. Now I'm going to do my pressure over pressure, kilopascals. So that's 239.4 kPa, which is already on top. It goes over 220.3 kPa on the bottom, which is already on the bottom. Notice I'm taking the number that's already in the numerator on top, and I'm just transferring to the top. The one on the bottom, 220.3, is already there. So I'm just transcribing this. Okay, so the kilopascals are left, and I'm left with 13 liters over 1. Or just 13. And that's my setup that you could see in a multiple choice. Notice the kelvins cancel. Notice kPa cancels. And you're left with liters, which is what we're trying to solve for. Now, it's nice to do it this way because it's really actually nice to solve for it. If you solve for it this way, you may forget to put these in parentheses, okay, to multiply. So I'm going to take my calculator And just follow with me. I'm going to take 253, and then as it says right here, I'm going to divide by 278. I'm going to hit enter. Now I'm going to times it by 239, 39.4. So I'm timesing that number by 239.4. And now I'm going to divide by 220.3. I'm going to hit enter. And now all I'm going to do is take that value and times it by 13 over 1, or just 13. Okay, and I get a number. And the number is 12.86. And of course, the only unit left standing is liters. Still using our units right from September into November. We're going to keep doing it all year long. Okay, now I have 4 sig figs here. 1, 2, 3, 4. I have 2. I have 2. I have 2. So this needs to be rounded to 2. So the answer is approximately 13 liters. Okay, that 8 is greater than 5, so it makes that number go up. So the answer is 13 liters, but I'm not done yet. Does this number make sense? Don't just come up with a number. Don't just be a robot and get numbers back. Does the number make sense? Well, let's go back into the problem. All right, let's go see what we have. We initially started with 13 liters. Okay, and notice we get back out 13 liters. Whoa, how did that work? We barely didn't change. Now, obviously, the raw answer was 12.8. We went down a little bit. But when you consider significant figures, significantly, we didn't change much. Why? Well, let's look at the problem. Okay, the pressure decreased a little bit. Now, let's pretend temperature stayed constant. I know it didn't, but just pressure alone. If temperature stayed constant in moles, if the pressure decreases, doesn't the volume increase? Isn't that a proportion? Isn't that an indirect proportion or an indirect relationship? That's Boyle's law. Yeah. So the volume should increase a little bit here if temperature stayed constant. I know it didn't, but just by the pressure dropping, the volume should increase a little bit. Okay. Now let's look at temperature independently, just like I did there. What I'm trying to do is make sense of this number. Okay, temperature decreased a little bit. So if temperature decreases, what happens to the volume? This is Charles' law, assuming pressure in moles, or assuming that pressure is constant. I know it's not, but just by temperature dropping, what would that do to the volume? And you can see that it would decrease it, right? Temperature and volume are directly related, whereas pressure, volume are indirectly. So you can see that the pressure decreasing, okay, would make the what? Volume go up a little bit because the pressure decreased a little bit. And you can see by the temperature decreasing, the volume would decrease a little bit. These two variables make the volume go up a little bit and decrease a little bit. And because they're going up a little bit and decreasing, they pretty much offset each other. And that's why we're left with what? Essentially the same volume that we started with, and that makes sense. I'm trying to make sense of the number that I have based on my intuitive understanding of these what? Individual relationships. So I'm asking you to solve for V, set it up, give me this setup, come up with a number, and of course make sense of it. What I'd like you to do now is go on to number 8. Try this one. Okay, stop me, see what you get, and then I'm going to talk about what I get compared to what you have. So stop me now. I can do this entire problem, and then I'll see what I get. So stop me now. Now, please stop me, and I'll start up soon. Okay, I'm back, and hopefully my work looks a lot like what you have. I always start with my formula. You can put the 1s in if you'd like. And you can put the 2s in if you like. It's not that important to me, as long as you know that this equals the current scenario and this is the future. So I put the current scenario together, 2.5 liters, 99 kilopascals. at 20 degrees Celsius. There it is, 293 Kelvin. I changed that. I have to be in a Kelvin temperature. Okay? Then I have what? 236 degrees Celsius is my new temperature. I had to convert that to Kelvin. Then I put my current, or I should say my new pressure to 94. What's the new volume? I solve for V by itself, brought the 509 Kelvin on top, then 94 to the bottom, and I have this expression. We rearranged our formula, what big boys and big girls do in this type of science, and then we rearrange one more time, put the like 2.5 liters by itself over 1 if you're more comfortable, 99 kilopascals over 94, how it's written here. It's how it's written here. Mathematically, this is equivalent. 509 over 293, like units over like units. And I do 2.5 times 99, enter, divide by 94, enter, times 509, enter, divide by 293, enter, and I get this raw number. I look back into my work and see that I have the least significant numbers. Looks like there's 2. So I round to 2, so 4.6 is my answer. I am not done. I'm not a robot. Now I'm going to see if the number makes sense. So let's see here. The pressure went down a little bit. So the pressure drops. The volume should increase because it's an indirect relationship, Boyle's law. So we should have an increase in volume, but not much because the pressure dropped a little bit, so the volume goes up a little bit. Then look at temperature. All right, temperature, wow, increases a lot, much larger. And how does temperature and volume relate? Well, those things are direct. So the volume should go up a lot. So if you look at this 293 to 509, it's a little less than doubling, but it's significant. Okay, so we have an increase in the volume by the temperature increasing a lot, and we have an increase in volume by the pressure dropping a little bit. So I would expect my volume to almost double in this case, and I start with 2.5 liters and I got 4.6. That makes sense. In this case, both variables changed to what? To both increase the volume collectively. So I'd expect a large increase. Now this temperature didn't quite double, but it increased significantly, and it was added to by the little bit of increase by the volume dropping, making my volume increase significantly. Less than half, but still significant. In the one above, okay, we had competing changes which canceled out. We were left with approximately the same volume. So this is the law. This is the combined gas law formula. You've been working with it for every single problem, except if you get all the variables, okay, you're not crossing out anything, and you're going to solve the exact same way. You're just going to have, more numbers involved. But everything else is the same. But I still want you to go through at the end of your problem to make sure that this number that you get intuitively makes sense. So please go through your homework. I think there's 1 or 2 questions left on that worksheet that are the combined gas law in nature, and go through with your key. Hopefully this helped.